All right, everybody. This is the makeup lecture from the Valentine's Day storm. We're going to be talking about stellar structure and evolution, but mainly today we're going to be talking about star formation, how stars form. But this is the beginning of the larger chapter that talks about the lives of stars. So I suppose the most important thing to know is that stars exist because of gravity. If it were not for gravity, we would not have stars. Okay? Stars are pulled together by gravity. Interstellar clouds of gas and dust contract into stars because of the force of gravity. If it weren't for gravity, the universe would be a thin, low-density conglomeration of nothing but hydrogen and helium. So gravity makes interstellar clouds contract into stars in the first place. It's gravity that makes stars shine. If not for gravity, stars wouldn't shine. It's gravity that squeezes a star's interior to the tremendous temperatures and pressures necessary for nuclear fusion. And it's nuclear fusion that powers the stars. Nuclear fusion is a very, very difficult thing to have happen. Fusing nuclei together to make heavier nuclei and to make energy in the process is something that only happens naturally in the centers of stars. Artificially, it also happens in the center of thermonuclear bombs, but that's not exactly a controlled situation. So again, gravity brings the clouds together in the first place to make stars. When the stars get hot in the interior because of the tremendous temperatures and pressures caused by gravity squeezing the star, then nuclear fusion happens and the stars begin to shine. Now, a star will not shine forever. Okay, a star's normal life when it's shining is a struggle against gravity. Gravity is still trying to make it collapse, but it generates enough energy to keep enough internal pressure to keep gravity from winning. Okay, so a star's life is a constant struggle against gravity, and it has to keep generating energy to battle gravity, basically to support its own weight. Otherwise, it will collapse even further. The thing about gravity, though, is that it's relentless. Okay, gravity always wins in the end. A star can fight valiantly for hundreds of millions or billions or even tens of billions of years, depending on the type of star. That's one of the things we're going to be talking about. But gravity always wins in the end. Okay, when a star runs out of fuel, it will collapse under its own weight and cease to exist as a star. It will become a former star, a stellar corpse, if you will. Okay. All right, so the main topic today is going to be the birth of stars. Okay, the birth of stars is a pretty interesting topic. Some astronomers spend their entire careers talking about the birth of stars. To have star birth, what you need is material to make stars out of. Luckily, there's a lot of material out there, and this material in general is called the interstellar medium, which I always found is a kind of a weird sort of phrase. It sounds something like a interstellar fortune teller. At any rate, we know for a fact that there's lots of interstellar gas and dust in our galaxy, especially in the disk portion of our galaxy. We're going to be talking about our galaxy later, but there's a disk portion and there's also a spherical halo portion that's more widely spread out. Okay. So how do we know this? Well, there's several lines of evidence that tell us this. There are places where we can actually see it very, very clearly and easily. One of these places is this here. This is called a dark nebula. Okay, a dark nebula, which I will outline in red here, looks like a gap in the stars. Okay, it looks like a gap in the stars. But it's not a gap in the stars. What it is a cloud of dust that's obscuring the light from all these stars behind it. Okay, you have this kind of curtain of stars in the background. You also have a cluster of stars over here. We don't know if that's in the foreground or the background. But basically, that cloud of dust is obscuring our view of the more distant portions of our galaxy. You can actually see this in the late summer, early fall, if you're in a really, really, really dark part of the, well, dark part of Pennsylvania, let's say. The Milky Way is kind of a curtain of starlight. You can't actually resolve the individual stars like you can here, but it looks like a milky band of light. And if you're in a really dark area and you see the Milky Way very clearly, you will see these dark lanes running through the Milky Way. You can actually see them on a very, very clear dark night with your naked eye. And those are actually dust clouds, you know, probably thousands of light years away, that are blocking our view of the more distant reaches of the Milky Way. Okay, so these things are called dark nebulae. Dark nebulae are cold dust clouds that block our view of distant stars. And that's one way that we know that there is interstellar gas and dust. Okay. Now, we've also mentioned that dust causes something called interstellar reddening, right? Interstellar reddening is a phenomenon that makes distant stars look redder. Okay, the analogy I used was it's kind of like the setting sun looks red when it goes down because of the dust within our atmosphere. All right. Also, that dust will make distant stars look dimmer than they ought to be. Now, because we don't know ahead of time how bright the stars should be, it's a little harder to tell that they're dimmer than they ought to be because, you know, we don't know ahead of time how bright they really are. However, what we can do is look at star clusters and estimate the brightness of typical star clusters. And what we find is more distant star clusters are dimmer than they ought to be. And we think that's because of something called interstellar extinction. Okay, interstellar extinction is also caused by dust particles, but it doesn't just change the color of the stars. It's also, because it's reducing the amount of light we're getting from those stars, it also makes the stars dimmer. Now, I mean, the two are connected. Interstellar reddening and interstellar extinction are basically two aspects of the same thing. The dust particles are reducing the red portion, are reducing the blue and green portion of the spectrum of the star. So not only will the star look redder, but the star will also look dimmer. Okay, so we know that dust is out there because of that. Okay. Also, sometimes if you look at the spectrum of distant stars, remember stars have absorption spectra, right? You have these rainbow type spectra with dark lines superimposed upon them. But sometimes there are extra lines. There are extra lines that are very, very narrow. And because they're very, very narrow, we know that they are caused by gas in interstellar space. So both of these things that we talked about here, the interstellar reddening and the interstellar extinction, is caused by dust. Okay. However, interstellar absorption lines, okay, are caused by gas. The gas causes the interstellar absorption lines. And so both things are evidence of what we call the interstellar medium. Okay, this medium of gas and dust that's out there in between the stars that provides us the raw materials to have stars be born. Okay. Also, sometimes you see clouds of bluish haze in the heavens. This is very hard to see with your eye because most of the time these bluish looking clouds like these down here are very, very dim. Okay, this is something called a reflection nebula. A reflection nebula is caused by dust scattering light from stars. So for example, there's a star here, and the starlight is going off in all directions, but it's surrounded by a cloud of dust. Okay, surrounded by a cloud of dust. And this cloud of dust tends to scatter light, and some of that light is scattered in the direction of us, direction of our eyes. And so we see this haze around the star. This is very, very similar to the sort of blue haze you see if you're unlucky enough to be in a smoky room. Luckily, there aren't as many smoky rooms as there used to be, but one of the few good things about a smoky room is you could see this effect. The dust particles are very tiny, and because of that, they tend to scatter the blue light in different directions, and some of that light gets scattered toward your eyes, and that lets you see the dust surrounding the star. Now, if you're looking at the star itself, if you're looking at just the star itself, you're going to see the spectrum of the star with some of the blue light left out. And so the star is going to look redder, but surrounding the star, the dust is going to look blue. Okay? So reflection nebula are dust clouds near a bright star that reflect this blue light. Okay? Let me see if I can, this sounds like a contradiction, but let me see if I can explain this with a drawing. Okay? Let's say we have a star, okay, right here. And surrounding this star are dust particles. Okay, lots and lots of dust particles. And I'm going to draw out these little dots here. Okay, those are the little dust particles. And our eyeball is going to be to the right here. Okay, our eyeball is to the right. We're on the Earth many, many, many light years away. And I'm going to pretend that the star only gives off blue and red light. Okay, so what I'm going to say is the star gives off red light, and the red light goes through the dust no problem. So we see the red light from the star, but we don't see any red light scattered from the dust either, because the red light just passes right through the dust. Okay, like that. The star also gives off blue light, and the blue light does get scattered by the dust. So the blue light that was heading toward our eyes gets scattered in a different direction. Okay, so instead of the beam of light from the star having blue light, that light is scattered away from us. However, and here's the thing, some of that blue light that's going in a different direction initially is scattered toward our eyes. Okay, like that. So the blue light bounces off some of the dust particles and ends up just randomly being scattered toward our eyes. Not all of it, but just some of it. And so what happens is, if your eyeball is looking directly at the star, you tend to see the beam, you see the star looking redder than it ought to. You see the beam of red light. If your eye is looking slightly off away from the star and looking at the dust surrounding the star, then you see the blue light coming toward you. Okay, so oftentimes this is what you'll see. If you have a star that's surrounded by a dust cloud, the cloud itself will look blue, but the cloud will make the star look redder. And that's why it seems like a contradiction that a dust cloud would be blue when we said that a dust cloud causes interstellar reddening. The thing is, it allows the red light through, so it allows the beam of light to look redder than it should be. It makes the beam of light look redder than it should be, but the cloud itself surrounding the star ends up looking blue in general. Okay. Now there's other type of nebula too. These are called emission nebula. The most famous, of course, is the Orion Nebula in the constellation of Orion. These are pink clouds of hydrogen gas, and these are near hot stars. So there are stars embedded in this nebula right here. It's ionizing the gas around it, and the gas is glowing pink, mainly because it's hot and it's mainly hydrogen, and the electrons are cascading down through the energy levels, and that's why you get this beautiful pink color. Okay, so generally anytime you see pink, diffuse pink clouds in the sky, it's from gas. Anytime you see diffuse blue clouds in the sky, like the area around this blue star right here, for example, that's dust. Often they're mixed together, so oftentimes you see bits of pink and bits of blue sort of interspersed, but the blue is caused by gas and the pink is caused by gas and the blue is caused by dust.